Good morning, everyone. Today we will see longest chain matrix multiplication using dynamic programming. First, we will see what is dynamic programming. It's a problem solving strategy. It includes a concept of overlapping subproblems. Here, dynamic programming concept can be used for finding optimal solution to the given problem. It is used to solve complex problems by breaking into small number of subproblems, and the subproblems can be solved individually. If the subproblems are repeated, occurred more than once, the results can be reused. Instead of doing repeated calculations, the results can be reused. It's particularly effective for optimization subproblems. We can find either maximum value or minimum value for some problems using recursive approach. The core idea is to solve each subproblem only once. If the subproblem occurred more than once, the problem can be solved only once and the result can be stored in a table. When a subproblem called, the answer will be reused. That eliminates redundant calculations that leads to efficient solution. And key components in dynamic programming, subproblems. The complex problem is divided into number of subproblems so that the time complexity can be reduced. What is optimal substructure? We have subproblem. Optimal solution to the subproblem can lead to optimal solution to the whole problem. That's called optimal substructure. Optimal solution for subproblems can be combined to get the optimal solution to the whole or complete problems. Overlapping subproblems. The same subproblems are solved multiple times in a Navy recursive approach. For example, Fibonacci n minus 1, n minus 2. If we solve Fibonacci of 5, the recursive approach, Fibonacci 2 occurred more than thrice. So instead of calculating again and again, the subproblems are solved and the results are stored in a table form. That is called memorization. That can be reused whenever subproblem occurs. And memorization is a concept storing the result of subproblems in a table so that the time complexity can be reduced from exponential to polynomial time. So exponential means 2 power n. That takes more time. That can be converted into polynomial n square n cube. So 2 power n computational complexity, exponential complexity reduced to polynomial n square n cube. That is the advantage of dynamic programming. And how we can apply dynamic programming concept to perform longest chain matrix multiplication. So we have multiple matrices. How it can be multiplied. For example, sequence of matrices A1, A2, An or matrices A1 or matrix, A2 or another matrix. How it can be multiplied. AI has dimensions. What's the dimension of matrix? Pi minus 1 into Pi. Find the minimum number of multiplications required to compute the product. Here the problem is to find number of multiplications to perform longest chain matrix multiplication, that is to multiply A1 to AN. And MCM, matrix chain multiplication, is a dynamic programming problem to find the most efficient way to multiply sequence of matrix. Here we are applying dynamic programming concept to perform matrix multiplication in a sequence form. And define TP, that is we are going to generate a table, dynamic programming table. TP is a two-dimensional table, dynamic programming with I number of rows and j number of columns that stores minimum number of multiplications needed to multiply matrix from AI to AJ. So for example, I is 1, J is equal to 4. We are going to multiply 4 matrix, A1 into A2 into A3 into A4. I is 1, J is 4. We are going to create dynamic table 1, 4. that the recursive relation can be T of I comma j is minimum of Tp of ik plus k plus 1 comma j plus I minus 1 into P of k into P of j. This is a recurrence relation to perform longest chain matrix multiplication is dynamic programming approach. Here we are going to find Tp using bottom up approach. The final answer is stored in Tp of 1 comma n. So we are going to generate two-dimensional table. In the table, we are going to find maximum, that is a minimum number of multiplications required to perform longer chain multiplication. That value is stored in a table TP 1 comma n location. And input matrices, there are 4 matrices A1, P 10 comma 3 dimensions, that is 10 rows, 30 columns. Matrix A2, 10 rows, 5 columns, 5 into 60. Here, the dimension of array is 10 comma 30 comma 5 comma 60. See, when we do multiplications, there's one constraint. Number of column in first matrix should be equal to number of rows in second matrix. See, the matrix A1, number of column is 30. That should be equal to number of rows in A2. And 5 columns in A2, that is equal to 5 rows in A3. So, total dimensions can be written as 10 comma 30 comma 5 comma 60. This means A1 dimension is 1030, A2 dimension is 35, and A3 dimension is 5 into 60. So from the given matrix, we are generating the dimension array called P. And dynamic programming table, so I comma j. So we are having 3 matrices. So 1 comma 2 comma 3. Here 1 comma 2 comma 3 is the size of the table. We are going to find number of multiplications required. So 1 comma n, that is 3 matrices. So the final result is stored in T of 1 comma n. So one first row, number of matrices 3. So 1 comma 3 is 4500. This is the number of multiplications performed to generate sequence, that is matrix multiplication of sequence of input matrices. And first step, define the dynamic programming table. TB I comma j, where the table stores minimum number of multiplications required to perform the matrix multiplication from AI to AJ. So base case is single matrices. For single matrix, multiplying single matrix has 0 cost. If you are having only one matrix, no need of multiplication. That is value will be 0. If you are going for more than one matrix multiplication, you have to find minimum number of multiplications. And step 2, compute dynamic programming table I comma j for increasing chain length. We using the formula. We are going to find the TP of I comma j value, where k determines the split matrix multiplication. So length is 2, pairwise multiplication. Calculate TP of 1 comma 2. So matrix A1 into A2. So multiply the dimensions for matrix 1 comma 2, 10 into 30 into 5. So the total number of multiplication is 1500. For 2 comma 3, to multiply matrix A2 with A3, number of multiplication is 9000. And length of 3, A1 into A2 into 3. So when we can take this one, there are 2 possibilities. A1 into A2. So we can multiply matrix A1 with A2. The resultant matrix can be multiplied with A3. In that case, multiply A1 into A2. The result already stored in a table. We know the value of T of 1 comma 2. So that is called dynamic programming approach. Already we have calculated value for TP of 1 comma 2. The value is 1500. And the result is multiplied with A3. So that will be 10 into 5 into 60. Total number of multiplication is 4500. And if second choice is, if we multiply A2 with A3, matrix A2 with A3, the result of A2 and A3 is multiplied with A1. In that case, already we know the value of TP of 2 and 3. Number of minimum multiplications required to multiply A2 and A3, that is 9,000, plus the result is multiplied with the A1, so that is 1,000, 18,000. So total will be 27,000. Choose the minimum value among step 1 and step 2, 4,500 and 27,000. Minimum is 4,500. So which is the best? We can multiply A1 with A2 first. Then the result will be multiplied with A3. Instead of going for step 2, step 1 performs minimum number of multiplications. So we can go for first option. That gives efficient way of calculations, that gives minimum time complexity. So time complexity is order of n power 3 due to 3 nested loops. So n is the size of the matrices, n power 3 is time complexity. And space complexity is we are generating TP, dynamic programming table I comma j, that is two-dimensional table. So time complexity will be order of n square. Time complexity is n square, space complexity is order of, so time complexity is order of n power 3 and space complexity is order of n squared, so two-dimensional table. This approach ensures that we minimize the number of multiplications and we can avoid repeated calculations using memorization. Thank you.